This sequence of videos is going to go through Newton's third law. So something to understand is that what we talked about in the previous video about interacting objects is also Newton's third law. So the bulk of the understanding of Newton's third law actually happens there. Here we're just going to formalize it a little bit, then talk about some applications and some subtleties that come in with acceleration constraints. So we're going to talk about how one actually calculates acceleration for interacting objects. And we're going to define acceleration constraints, which is an important idea that will also come up in the next section about ropes and pulleys. And then we'll renew our problem-solving strategy for interacting object problems, so that will be at the very end. And the main learning outcome for this actually has to do with problem solving. So the focus is going to be how do we do calculations. So a lot of what we've talked about in the past is the conceptual part, and now we're focused more on the calculations. So, Newton's third law. What is it, even though we've been using it? So the quote, if you will, is that every force occurs as one member of an action-reaction pair of forces. So the classic phrasing is something along the lines of, for every action there's an equal and opposite reaction. And the book doesn't care for that phrasing, and neither do I, because again, our action-reaction pair of forces is symmetric. It isn't that one happens first and then the other happens. They arise together, and it's always a pair. One is not the action and the other the reaction. It's a pair of forces, but we typically call it action-reaction because there's one that you start with and then you say the other one must be there. But that's just the order that you're going in, not any sort of order that is essential to nature. So the other thing that's important about this is that every force is occurring as part of this pair. So again, in the past, in one of the previous videos, we talked about creating those interaction diagrams, and that if you have any lines connecting objects within your system, that you expect to find both parts of the pair. But if the line is connecting an object in your system to an object in the environment, that you only find one force. The other force does exist, but it's actually acting on something in your environment, so you don't worry about it in your problem. So a couple of rules about this, most of which I think have already come up, but which are important enough to say again. Each force, every force, in an action-reaction pair acts on, I don't know why that says actions, acts, that's the word, it's called acts, on a different object. So why that matters is that when you have a pair, that cannot, each of these pairs, right, you have force 1 and force 2, they have to be acting on different objects. They cannot be acting on the same object. If you think you identify an action-reaction pair, but both forces act on the same object, you are incorrect. So make sure that when you are identifying your action-reaction pair of forces, or your Newton's third law pair, as I frequently call them, they must be acting on different objects. One object is the agent for the other one, and vice versa. It's symmetric. So each force in this pair is equal in magnitude, but opposite in direction. And I'm saying each here, but I mean each of two. It's a pair. So it's equal in magnitude, opposite in direction. And so this is where you can just plop a minus sign in front of the vector, because that's what minus signs on vectors do. They preserve the magnitude, but flip the direction. Now the last thing that I think is important to highlight, and the book doesn't highlight quite as much, is that these two forces are of the same type. And what I mean here is that in your pair of forces, if one is a gravitational force, the other is a gravitational force. If one is a push, the other is a push. If one is a pull, the other is a pull. If one is tension, the other is tension. If one is friction, the other is friction. And so on. So it's really important to think about that, since again, it will help you not incorrectly identify the Newton's third law pair. So please be careful about that. Same type, and again, going to be equal and opposite in direction and magnitude. Okay. So that's it for Newton's third law. Again, these are ideas that we've already been talking about in previous videos. This is just formalizing it a little bit and calling it Newton's third law.